Hello, welcome to AMD EDF Linux Operating System Integration and Development using the AMD Embedded Development Framework how-to video. Here, you will use a pre-built Yocto project framework to generate the EDF Linux disk images and artifacts used in the Getting Started with the AMD EDF and Developing Software with the AMD EDF videos. The OS developer builds custom images to meet system or application needs, ranging from simple Linux builds to complex setups with hypervisors, containers, or multiple domains. This includes low-level components like PMU, PLM, PSM firmware, U-Boot, and ARM-trusted firmware. The Yocto project provides the environment to create these custom heterogeneous boot and OS images. This video begins by demonstrating the necessary steps required for setting up and configuring the Yocto project environment. Then, you will create a single-stage EDF Linux disk image for VEK280 board, which is based on the Versal AI Edge series. And you will also generate a multi-stage EDF Linux disk image, including the OSPI binary image required for VEK385 board, which is based on the Versal AI Edge series Gen 2. Note that if the board you are working with is a production board, it will be pre-programmed with an OSPI image. Finally, you will configure a QEMU environment and run the emulation on QEMU. You will also build and install a customized SDK for cross-development of your application. This video assumes you are using a supported operating system for the Yocto project environment. At this stage, basic to advanced Yocto project knowledge is required depending on the task you want to perform. Please refer to the Yocto Project Basics video for learning more about the Yocto project environment. Here you will use the repo tool, which is a tool chosen by AMD to be the tool for EDF flows to manage multiple Git repositories. First, you will configure Git with your username and email, and then set up the Yocto project environment. The operating system integration and development flow for AMD Versal devices demonstrated in this video is also available in text form in the Operating System Integration and Development wiki page. Let's begin the demonstration by setting up the Yocto project build environment. This guide assumes that the build host shell is bash, not CSH or dash, and the OS is supported by Yocto project. Configure your Git identity. Use your identity. Do not follow these commands word for word. Run git config globaluser.email followed by your email. Then set your name with git config globaluser.name followed by your name. Confirm this configuration using git config list. Download and install the repo tool using curl, which will help you to set up all the necessary repositories for EDF. Use the command curl storage.googleapis.com/git-repo-downloads/repo. Ensure that the downloaded binary is executable by using chmod a+x. Then, create and add repo to your bin directory. Ensure that this bin directory is appended to your path variable using path equals tilde/bin:\path. Create a directory for the EDF project and navigate into it. Now clone the Yocto project metalayer source using repo init. Use the latest EDF version tag when pointing to the Yocto project manifest. Here, it is version 25.05. Fetch by using repo sync. This may take a few seconds. When done, set up your build environment by sourcing the EDF init build env script. If you are on an NFS-based build host system, modify the build/conf/local.conf configuration file and add a tmpdir variable pointing to a temporary directory. When the environment is fully set up, it is time to begin generating the files necessary for booting the device. A single-stage boot image will be generated for the AMD Versal AI Edge series, VEK280, so that the necessary files are created to successfully boot via a properly partitioned SD card. First, the binary boot file must be generated. To do this, run machine equals Versal v EK280 SDT seg bitbake Xilinx boot bin. This command uses the VEK280 board layer to run the Xilinx boot bin recipe. When completed, generate the SD WIC. To do this, run machine equals AMD Cortex A72 common bitbake EDF Linux disk image. This command uses the ARM Cortex A72 meta layer to run the bitbake EDF Linux disk image recipe. After completion, all required files are created and exist in the TMP deploy images directory. If you use the default TMP directory, it is created and accessible from the build directory. The GUI is used to verify the boot.bin was generated properly by looking in the Versal VEK280 SDT seg directory. Here you can find the boot.bin file. It should be approximately 3 to 4 megabytes if you are following this exact build. Next, to ensure that the EDF Linux common disk image .wic file was properly created, look in the AMD Cortex A72 common directory. Here, you can find the EDF Linux disk image AMD Cortex A72 common.rootfs.wic file. It should be approximately 9 to 10 gigabytes if you followed this exact build. After verifying that files were successfully generated, the SD card.wic file must be partitioned to add the bootloader. To do this, first confirm that the content of the EFI partition of the .wic file is empty by running the wic-ls command on it with :1 attached to the end of it. Make sure there are no files attached. Now, copy the boot.bin into the EFI partition of the wic image by running wiccp, the boot.bin file, then the .wic file with :1 at the end to indicate the EFI partition. List the .wic file's EFI partition out again to confirm that the boot.bin was successfully added. This partition .wic file can then be flashed onto an SD card and used to boot a single-stage bootloader board like the VEK280. Now, images and binaries for a Versal AI Edge series Gen 2 VEK385 will be built. The VEK385 follows a multi-stage boot process by default. This means an OSPI binary image that contains boot firmware and boot images is created for the first stage bootloader. Then, a common EDF Linux disk image is created for the next stage of the full OS image boot. These files can again be generated using the bitbake command attached to a recipe. Note that production boards are shipped with the OSPI populated, but this process must be followed if the firmware bundles that affect the initial boot were modified. Let's generate the board-specific OSPI binary image containing the boot firmware. To do this, run machine equals Versal 2VE 2VM VEK 385 SDT seg bitbake EDF OSPI. This command uses the VEK 385 board layer to run bitbake's EDF OSPI recipe. This command can take roughly 30 minutes to an hour or longer, depending on the performance of the build host PC. Once completed, let's generate the common EDF Linux disk image, SDWIC. To do this, run machine equals AMD Cortex A78 Mali common EDF Linux disk image. This command uses the ARM Cortex A78 meta layer to run the bitbake EDF Linux disk image recipe. Again, this command can take 30 minutes to an hour or longer, depending on how powerful your build host is. After completion, both required files are now created and exist in the TMP deploy images directory. If you use the default TMP directory, it is created and accessible from the build directory. To verify the OSPI boot file was generated, look in the Versal 2VE 2VM VEK 385 SDT seg directory. Here you can find the EDF Versal 2VE 2VM VEK 385 SDT seg.bin file. It should be approximately 270 megabytes if you were following this exact build. Next, to ensure that the SDWIC file was properly created, look in the AMD Cortex A78 Mali common directory. Here you can find the EDF Linux disk image AMD Cortex A78 Mali common .rootfs.wic file. It should be approximately 9 to 10 gigabytes if you followed this exact build. These OSPI and SD card WIC images can now be flashed and used to boot a VEK 385. Refer to the Getting Started with AMD-EDF video for more information. Quick Emulator, or QEMU, can be used to simulate the generated OSPI and WIC images. Create a directory and copy the common images to this new directory. Use the bundled QEMU boot tool to merge the two images as can be seen on screen. This is required since to run the QEMU, only one config file is accepted rather than the two that are created through the build. This can be done with the shown command. Once done, verify the contents of the file using the cat command. Launch the QEMU boot instance using the command run QEMU. The QEMU instance will boot up using the images. Log in using the default username AMDEDF and set up your password when prompted. Explore the running system by listing out the programmable logic PL firmware files included by running DFX Manager Client -list package. Exit QEMU typing Ctrl-A and then X. In the Developing Software with AMD-EDF video, we use the pre-built EDF SDK to compile and deploy an Hello World application. However, we noted that this SDK was not extensible, and adding new packages means that a new SDK will need to be built. This process begins by first modifying the SDK recipe in the Meta EDF app sdk.bb file, found in the directory /yocto/edf/sources/meta amd edf/recipes core/meta. Append recipes to the toolchain target task list. Now, build the SDK using machine equals AMD Cortex, A78 Mali Common Bitbake Meta, EDF App SDK. The resulting SDK install script will be placed in the tmp/deploy/SDK directory. To run the SDK, execute the generated script in the tmp directory. Enter the target directory when prompted. Once completed, the SDK was successfully installed. In this video, the necessary steps for configuring the Yocto project environment were shown. Next, an EDF Linux disk image for an AMD Versal AI Edge Series VEK280 board and an OSPI binary and EDF Linux disk image for a Versal AI Edge Series Gen 2 VEK385 board was generated through a series of Yocto project commands and recipes. Then, we used the files created for the VEK385 to boot and emulate the board using QEMU. Lastly, an SDK for application cross-development was built and installed.